Hello everyone and welcome to my channel. If you already know Python basics but feel stuck when it comes to writing clean, efficient and professional level code, then this course is exactly for you. In this video, I'm excited to introduce my brand new course, Advanced Python Programming Template course. This course is designed to take you beyond the basics and help you think like a professional Python developer. We won't just learn what Python feature exists. We'll focus on why they work, how they're implemented, and when to use them in real-world projects. By the end of this course, you'll be writing Python code that is clean and readable, Pythonic and maintainable, efficient in terms of performance and memory. Chapter 1, Introduction. We'll start with a quick course introduction and then set up all the required tools and environment so everyone is ready to follow along smoothly. Chapter 2, Data Types and Numbers. In this chapter, we go deep into numbers and data types. Type conversion, number-based conversion, representing numbers in different bases, writing readable numeric constants. You'll learn how Python actually handles numbers behind the scenes. Chapter 3, Boolean Logic. Here we cover truth values of variables, short circuit behavior of and or. This chapter helps you write a smarter condition and avoid subtle logic bugs. Chapter 4, Strings Mastery. Strings are everywhere in Python, so we've mastered them completely. Classic string construction, %formatting, str.format, f-strings, template strings, ord and chr functions. You'll understand every modern way to work with strings. Chapter 5, Naming Conventions. Professional Python code follows convention. We'll cover single underscore usage, leading and trailing underscore, double underscore names, magic methods. This chapter alone will level up how your code looks and feels. Chapter 6, Essential Python Functions. We'll explore powerful builds like any and all, min, max, sum, and len, hash, and real-world use cases, shallow vs deepcopy, precise calculations using decimal. Chapter 7, Logging. Learn how to use logging the right way, logging fundamentals, advanced logging configuration. This is critical for real production applications. Chapter 8, Iterables. We dive deep into iterables and iteration tools. Map, filter, sorted, reversed, enumerate and zip, iter and next, range and slicing. Chapter 9, Practical Data Structures. You'll master advanced data structures from the standard library. NamedTuple, counter, defaultdict, OrderedDict, ChainMap, deque, array module, MappingProxyType. These tools help you write faster and cleaner code. Chapter 10, Comprehensions. We cover list, set, and dictionary comprehensions, generator expressions. You'll learn how to write powerful one-liners without sacrificing readability. Chapter 11, itertools module. This is where Python gets really powerful. Infinite iterators, zip longest, accumulate, chain, filter false, pairwise, StarMap, product, permutation, and combination. Chapter 12, Functions in Depth. We go deep into functions, function definitions and features, functions as arguments and return values, callable classes, args and quarks, positional vs keyword only arguments. Chapter 13, Generators. You'll learn generators with yield, generator expressions, generator classes, performance and memory comparison, perfect for writing efficient, scalable code. Chapter 14. Decorators. Decorators can be confusing, not anymore. Decorator fundamentals. Decorators with arguments. Combine and parameterize decorations using the decorator module. Chapter 15. Functools module. We explore cache and LRU cache. Partial functions. Reduce. These tools help optimize and structure your code. Chapter 16. Enum classes. We cover defining enums, adding operators, auto values, the unique decorator. Chapter 17. Object-oriented programming. Finally, we master advanced OOP concept, instance, class, and static methods, abstract base classes, the property decorator. Why this course? By taking this course, you will write production-ready Python code, master advanced built-in module and tools, improve performance and memory efficiency, understand Python internals deeply, become confident in real-world Python development. If you are ready to move from knowing Python to thinking like a Python developer, this course is for you. Make sure to subscribe to the channel and let's start writing better Python code together. Hi everyone, welcome to this tutorial. Today I'll show you how to set up your Python programming environment on your computer, step by step. We'll start with Visual Studio Code, then install Python, and finally set up the Python extension. Let's get started. Step 1. Installing Visual Studio Code. First, we need a code editor. I recommend Visual Studio Code, or VS Code for short. VS Code is free, lightweight, and work on Windows, Mac, and Linux. Go to the official VS Code website, code.visualstudio.com. Click on the download button for your operating system. Once the download is complete, run the installer. Follow the on-screen instructions and finish the installation. After installation, open VS Code. You will see the welcome screen with option to open a folder or create a new file. Step 2. Installing Python. Next, we need Python itself. Python is the programming language we'll be using. Open your web browser and go to the official Python website, python.org. Click on the downloads menu and select the version recommended for your operating system. Usually it will suggest the latest stable release. Download the installer and run it. Make sure to check the box that says add Python to path before clicking install. This is very important. After the installation is complete, you can verify it by opening a terminal or command prompt and typing Python version. It should display the installed Python version. Step 3. Installing Python extension in VS Code. Now that we have Python installed, we need to add the Python extension in VS Code. This makes coding much easier. Open VS Code, go to the extension panel on the left. The icon looks like a square. Search for Python by Microsoft and click install. Once installed, VS Code will automatically detect your Python installation. You're now ready to create Python files and start coding. And that's it. You now have a complete Python programming environment set up. VS Code, Python, and the Python extension. You're ready to start coding and exploring Python. If you found this tutorial helpful, don't forget to like and subscribe for more Python tutorials. See you next time. Hello everyone, welcome back. In this session, I want to talk about different ways to convert data type in Python. Let's start with a simple example. First, I create a variable called a and assign it the value 10. Right now, a is a string. Next, I want to convert a into an integer and store it in a new variable called b. So I write b equal int a. This command converts the value of a into an integer and stores it inside b. Now, if I print the type of b, print type b, and run the program, you can see the output that it shows class int. That means b is now an integer. Next, I'll create another variable called c and assign it a numeric value, for example 20. Now I want to convert this integer into a string. I do that by writing d excuse me, d equal strc. If I print the type of d, print type d and run, as you can see in the output it says class str, which means d has been converted into a string. And if I print the value of d, print d, you'll see 20 printed in the output. Now let's talk about float conversion. Suppose I have a variable called x with the value 15.5. Right now x is a string. If I want to convert this string into a float, I write y equal float x. This command converts the value of x into a floating point number and stores it in y. If I print the type of y, print type y and run, you'll see that is class float. So now y is a float data type. Also, we can convert an integer into a float. For example, if I write z equal float c, that's it. The integer value 20 will become 20.0. Now let's look at Boolean conversion. Suppose we have a variable e which is a string with the value true. To convert this string into a Boolean, we write f equal bool e. If I print the value of f and run, it will print true. And if I check the type of f, print type f, it will show class bool. So this is how we can convert different data type in Python: a string to integer, integer to a string to float, integer to float, a string to Boolean. One important point to remember is that the value must be convertible. For example, if we have a string like Alex, we cannot convert it into an integer or a float. as long as the value is valid and convertible. We can easily change data type using these methods. I hope you enjoyed this lesson. See you in the next session. Goodbye. Hi everyone, and welcome to another Python tutorial. Today we are going to dive into working with different number bases in Python. First off, let's define a variable and assign it the value of 12. In Python, when you write a number like this, it's implicitly in base 10. Let's run it and print 12. Okay. Now, let's see how we can represent the same number 12 in base 2, base 8, and base 16. To define a number in base 2 or binary, we use the prefix 0b. So, 12 in base 2 is 0b1100. Let's run it and print 12. Okay, for base 8 or octal, we use the prefix 0o. 12 in base 8 is 0o14. Let's run it and print 12. And for base 16 hexadecimal, we use the prefix 0x. 12 in base 16 is 0xc. Let's run it and print 12. As you can see, the output for all this is 12. This means Python correctly interprets these prefix value and converts them their base 10 equivalent internally. Let's demonstrate this equality by comparing them. We'll compare the base 10 value of 12 with the base 16 value 0xc. Run it and print true. The result is true, indicating they are indeed the same value. Now, what if you have a base 10 number and want to see its representation in other bases? Python provides built-in function for this. The bin function converts base 10 integer to its binary base 2 string representation. Let's run it and print 0b1100. Okay. The oct function converts base 10 integer to its octal base 8 string representation. Run it and print 0 or 14. And the hex function converts a base 10 integer to its hexadecimal base 16 string representation. Let's run it. Let's print 0xc. Finally, how do we convert numbers from base 2, base 8 or base 16 back to base 10? We can use the int function by specifying the base of the input string. They convert a base 2 number string to base 10. Let's run it and print 12. 1100 print 12. They convert a base 8 number string to base 10. Let's run it and print 12 again. And to convert a base 16 number string to base 10, let's run it and print 12 again. As you can see, the int function is very versatile for converting a string representing numbers in different bases back to base 10 integers. I hope you found this tutorial helpful. If you have any question, feel free to ask in the comments. See you in the next video. Hello again everyone. In today's video we are going to explore another neat way to work with different number bases in Python. In our previous video we learned how to define number and convert them using bin, oct and hex. But there's an even more concise method. Let's start by defining a variable and assign it the value 12. Let's print. Let's run it and print 12. Okay. Now we want to display this same number in base 2, base 8 and base 16, but this time using f string. This approach is very readable and efficient. To display the number a in base 2, we use the format specifier a:b. Let's print it and let's run it and print 1100. Okay. Now for base 8 we use the format specifier a:0. Let's run it and print 14. And for base 16 we use format specifier a:x. a:x. Let's run it and print c. Okay, but what if we want Python to recognize these as literals, meaning with the prefixes 0b, 0o, and 0x. To do this, we simply add a hash symbol before the base specifier letter. For base 2 with a prefix, we use a:#b. Okay, let's print it. a:#b. Okay, let's run it and print 0b1100. Let's run it. 0b1100. Okay. For base 8 with a prefix, we use a:#o. a:#o. Let's run it and print 0o14. And for base 16, with a prefix, we use a:#x. Let's run it and print 0xc. As you can see, with this method, we have easily printed the number 12 in base 2, base 8, and base 16, both without prefixes and with the standard Python prefixes 0b, 0o, 0x. This is incredibly useful when you need to quickly display numbers in different formats, especially during debugging. So remember that in addition to the bin, oct, and hex functions, you can also leverage f-string formatting to represent numbers in various bases, and by adding the hash symbol, you can even display the specific prefixes for each bases. I hope you found this new trick helpful. We'll be back with more exciting Python topics in future videos. Goodbye. Hello again to all Python enthusiasts. Continuing our educational series, today we are going to focus on a crucial tip for writing more readable code, using the underscore as a digit separator for numeric literals. You might have encountered a large number in your code before, like 1 million. Reading such a number, especially when it gets longer, can be tiring for the eyes and increase the chance of errors. The problem: reading long number like 1 million can be difficult. Python's solution: from now on, when you need to define a large number, you can use underscore between its digits. Python will ignore these underscore and only process the actual numeric value. Let's see how this works. Suppose we want to define the number 1 million. We can write, and let's print, and let's run it and print 1 million. Or even for a large number like 1 billion, Let's run it, let's print it, and let's run it and print 1 billion. As you can see, Python has ignored the underscore and correctly stored the numeric value. This makes our code significantly more readable. This feature isn't just for regular integers. It's also applicable to floating point numbers and for representing numbers in different spaces, binary, octal, hexadecimal. For instance, imagine a long hexadecimal number that's hard to read with the 0x prefix and no separator. Let's print it and let's run it and print it. Okay, or a long binary number. Let's print it and let's run it and print it. And similarly for octal number. Let's run it, print it, and let's run it. Print it. Okay. Just as expected, Python ignores the underscore in these numbers as well and displays the correct value. This feature greatly enhances code readability and maintainability, especially in code bases that deal with many large values. So remember to use the underscore digit separator to improve your code's readability the next time you encounter large or complex number in Python. Until our next video, happy coding! Hello everyone! In Python, the logical operators and or are used to combine conditions, but they behave differently depending on the truth value of each condition. The AND operator. When you write an expression like W and Z, the result will be true only if both W and Z are true. In all other cases, the result is false. The OR operator. When you write W or Z, the result will be false only if both W and Z are false. In every other case, the result will be true. Short circuit behavior. Both and or use something called short circuit evaluation, meaning Python sometimes doesn't evaluate the second condition at all. Short circuit in an expression like condition 1 and condition 2, if condition 1 is false, Python does not evaluate condition 2 because the final result will definitely be false, regardless of the second condition. Short circuit in OR. If condition 1 is true, Python skips condition 2 because the final result will be true, no matter what the second condition is. Why short circuiting matters? Short circuiting is especially useful when you know that the first condition is cheaper to compute. For example, if condition 1 is a simple comparison But condition 2 involves calling a function or performing a heavy calculation. Placing the cheaper check first can make your code more efficient. Goodbye. Hello again to our regular viewers. Today we are going to introduce two very practical and interesting functions in Python, ord and chr. These two functions act as a bridge between the world of characters and the world of numbers. The ord function. This function takes a single character and returns its corresponding Unicode numerical value. Simply put, it tells you the numerical code each letter or symbol has in the computer world. The chr function. This function does exactly the opposite of ord. It takes an integer and returns the character corresponding to that code. As you can see, these two functions are inverses of each other. If you convert a character to a number using ord and then pass the same number to chr, you will get the original character back. Let's clarify this with a few examples. Example 1. Converting alphabet letters. We want to find the numerical code for the uppercase letter A and then see what the code for the lowercase letter A is. I define a variable and assign it uppercase A. Then I define a variable and assign it or the char underscore A. Let's print it. And let's run it and print 65. Then I define a variable and assign it lowercase a and define a variable and assign it or char underscore a. Let's print it and let's run it. 97. Now let's try the inverse. Is chr65 the same as uppercase A? Let's print it. And let's run it, and yes, uppercase A. Is chr97 the same as lowercase a? Let's print it. And let's run it. Yes, lowercase a. As you can see, uppercase and lowercase letter of the English alphabet have different numerical codes. Example 2. Converting a special character and symbols. These functions aren't just for letters. Let's find out the numerical code for the exclamation mark and the euro symbol. Let's print it. Example 2. I define a variable and assign it exclamation mark. Then I define a variable and assign it ord char underscore exclamation. Let's print it and let's run it. Print 33. I define a variable and assign it euro I define a variable and assign it ord char underscore euro. Let's print it and let's run it and print it. Okay. And their inverse. Let's print it and let's run it. Okay, print it, another print, and let's run. Euro symbol is printed. Okay, this demonstrates that ord and chr can work with a wide range of characters. Example 3, creating a symbol an encoded message. Let's say we want to encode a simple message by shifting the numerical code of its characters in a very basic way. For instance, we can shift each letter to the next character in the Unicode table. Let's do this. I define example 3. I define a variable and assign it hello. I define a variable and assign it empty string. I define another variable and assign it empty string. Let's print it. Print hello. Okay. Encoding the message. Let's do this. Let's print it and let's run it and print it. Okay, decoding the message. Let's print it. Let's run it and print hello again. Hello. Okay. This was a very simple example of encoding, showing how we can perform interesting operations on strings by combining ord and chr. Important note: the ord function accepts only a single character. If you pass a string longer than one character, you will get an error. Similarly, the chr function accepts only integers, and these integers must be within the valid range of Unicode code points. I hope this example have helped you better understand the utility and power of the ord and chr functions. See you in the next video. Hello everyone. In Python, the underscore character plays a significant role in naming convention for variables, functions, and methods. While Python itself doesn't strictly enforce all these conventions, they are widely adopted by the community to improve code readability and single intent. Let's break down the different ways underscore are used. Number 1. Single leading underscore. Convention. Variables or methods prefixed with a single underscore are considered internal use or protected. This is a hint to other developers that these members are not part of the public API of a module or class and should not be accessed directly from outside unless you know what you are doing. Behavior. Python doesn't strictly prevent access. However, during from module import star, imports names starting with underscore are not imported into the current namespace. Let's do this. Number 1. usage. Let's print it. Let's run it and print 10 and 20. Okay, number 2, double leading underscore. Convention: when a variable or method name within a class starts with 2 underscores and doesn't end with 2 underscores, Python performs name mangling. This is primarily used to avoid naming conflicts in classes that inherit from each other. Behavior: Python automatically renames these attributes to underscore class name underscore underscore variable. This makes them harder to accidentally override in subclasses. Let's do this. Number 2. Excuse me. Let's print it. And usage. Let's print it. Let's print it. Let's run it and print 10 and 30. Okay, number 3, double leading and trailing. Convention: these are special or magic methods and variables in Python, often referred as dunder methods. Dunder is double underscore. They are used by Python itself to implement a specific behavior. You should not invent your own names following this pattern. Instead, you use these to hook into Python built-in functionalities. Example: underscore underscore init underscore underscore constructor underscore underscore str underscore underscore string representation underscore underscore len underscore underscore length underscore underscore add underscore underscore addition operator. Example number 3. Excuse me. Okay. Excuse me. Excuse me. Excuse me. Okay, let's print it. And let's run it and print it. Okay. Number 4, single trailing underscore. Convention. This convention is typically used to avoid conflicts with Python reserved keywords. For instance, if you wanted to name a variable class, you couldn't because class is a keyword using class underscore solves this behavior. This is purely a naming convention to avoid syntax errors. Let's do this. Number 4. You cannot do this. Instead, use a trailing underscore. Let's print it. And let's run it. And class type printer. Okay. Number 5. Single underscore in the middle convention. This is the standard way to create readable variable names using multiple words in Python. Now, as a snack case, it's highly recommended for all public variables, functions, and methods. Behavior improves code readability significantly. Let's do this. Number 5. And let's print it. And let's run it and print. Okay. Underscore variable convention for internal use. Underscore variable name mangling to avoid naming conflict in inheritance. Underscore variable underscore special methods variable recognized by Python. Variable underscore avoid collision with Python keywords. Variable underscore name standard multi-word variable naming snack case. I'll see you in the next video. Hello everyone. The any function returns true if at least one element in an iterable like a list, tuple, or set evaluates to true. If all elements are false or the iterable is empty, it returns false. Mental model: at least one true result is true. All false result is false. Example: print any true, false, false. Output true. Print any 0 empty string none. Output false. All are considered false in a Boolean context. Print any 0 1 0. Output true because of the number 1, which is true. Note: in Python, the following values are considered false. Evaluate to false in Boolean context: 0, 0.0, empty string, empty list, empty dictionary, none, false. The all function in Python. The all function returns true if all elements in an iterable evaluate to true. If any element is false or the iterable is empty, it returns false. Mental model: even one false result is false. All true result is true. Example: int all true true true. Output true. Int all true false true. Output false. Int all 1 hello and 1 2 in a list. output true. All elements are considered true in a Boolean context. Let's run it. True, false, true, 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 false, true, true, false, true in a output. The core difference between any and all. Any looks for at least one true. All looks for no false, meaning all must be true. A comparative example. I define a variables and assign it 1, 2, 3 in list and print any n higher than 2 for n in nums true because 3 is greater than 2. Print all n higher than 2 for n in nums false because 1 and 2 are not greater than 2. Let's run it. And true, false. See you in the next video. Hey everyone, and welcome back to the channel. Today we are diving into two incredibly useful yet super simple Python functions, min and max. These functions are your best friends when you need to quickly find the smallest or largest item in collection of data. Ready to unlock this Python superpower? Let's go. Part 1. The min function, finding the little guy. Imagine you have a list of student scores and you need to find the absolute lowest score. That's where min shines. This function takes an iterable like a list, tuple, etc. and returns the smallest item within it. Example 1. I define a variable and assign it a list. I define a variable and assign it min scores. Let's print it and let's run it and print 3. Another example. I define a variable and assign it CAZBY and define a variable and assign it min letters. Print it, run it, and print A. Okay. See, min instantly I defined 3 as the smallest number. It even works with letters, returning lowercase a, because it comes first alphabetically. Okay, part 2. The max function, reaching for the top. Now, what if you want the highest score? Or perhaps the maximum temperature recorded over a week. That's where max comes to the rescue. I does the exact opposite of min, finding the largest item in a sequence. For example, example 1. List of numbers. I define a variable and assign it a list. I define a variable and assign it max scores. Print it and let's run it and print 89. Another example, list of character. I define a variable and assign it CAZBY and define a variable and assign it max letters. Let's print it. Let's run it and print lowercase z. Okay, and just like that, max gives us the highest score, 89, and the letter z, which is last in alphabetical order. Part 3, cool use cases and pro tips. These functions aren't just for lists. You can compare individual item directly. Let's print it. Let's do this. I define a variable and assign it 150. I define a variable and assign it 200. Let's print it. Let's run it and print the smaller of 150 and 20 is 150, and larger of 150 and 2000 is 2000. Here's a pro tip. Min and max work with any data type that supports comparison, like strings, tuples, and even dictionaries. Want to level up? Use the key argument. This is super powerful for finding the minimum or maximum based on a specific criterion, like finding the student with the highest score in a list of student dictionaries. Let's do this. I defined a variable and assign it a list. Excuse me. Find the student with the highest score. I define a variable and assign it max students and key. Assign lambda student colon student score. Let's print it. And let's run it and score 92 here. Okay, find a student with the lowest score. I define a variable and assign it min students key lambda student colon student score. Let's print it. And let's run it. Score 78. Conclusion. So there you have it. Python min and max functions, simple, powerful, and ready to streamline your code. You can now easily find extremes in your data. If you found this video helpful, please give it a thumbs up, subscribe for more Python tutorials, and hit that notification bell so you don't miss out. Got question? Drop in the comments below. Thanks for watching and happy coding. Hey everyone, welcome back to the channel. In today's lesson, we are going to explore two incredibly useful Python functions that every beginner should master: sum and len. These two functions help you analyze and work with data faster and more efficiently. And trust me, you will use them all the time. So let's dive right in. Part 1. Understanding sum, your personal calculator. Whenever you need to add up a list of numbers, whether it's total sales, total scores, or even the calories you ate today, sum is your simple one-line solution. Example: I define a variable and assign it a list. I define a variable and assign it some scores. Let's print it. Let's run it and print 105. Sum takes an iterable like a list, tuple, or set and returns their total. Here it adds all the numbers and returns 105. Adding a string value. Did you know sum can start from a custom value? This is great when you want an offset. Example: I define a variable and assign it a list. I define a variable and assign it sum, price, and 50. Okay, let's print it. And run it and print 650. Okay. Important tip. Some work only with numbers, not as strings or mixed data types. For those, you will need other techniques. Part 2. Understanding len. Count anything. Len returns the number of items in a collection. Think of it as Python built-in counter. Example: count item in a list. I define a variable and assign it a list. I define a variable and assign it len students. Let's print it. Let's run it and print 4. 1, 2, 3, 4. Okay, another example: count characters in a string. I define a variable and assign it hello Python. I define a variable and assign it len message and print it. Let's run it and print 30. 13. Okay. Another example. Count keys in a dictionary. I define a variable and assign it a dictionary. Excuse me. Okay. Let's print it. And let's run it. And print 3. Part 3. Combine sum plus len for real use case. Now, here's where the magic happens. You can combine both functions to analyze data super fast, like calculating averages. Another example, calculate the average score. I define a variable and assign it a list. I define a variable and assign it sum scores, division, len scores. Let's print it. And let's run it. 20. Okay. Part 4. Real world. Example, student grades. Example, real world. Example, student grade. I define a variable and assign it a list. I define 3 dictionary. Excuse me. Extract only the scores. I define a variable and assign it a student scores for a student in students. Okay, I define a variable and assign it sum scores, division, len scores. Let's print it. Let's run it and print 85. Okay. Using a list comprehension, when extracted student scores and calculated the average using, you guessed it, sum and len. Conclusion. That's it for today. You just learned 2 simple but powerful tools. Sum for adding values and len for counting items. These 2 functions are going to be with you throughout your entire Python journey. If you enjoyed the video, don't forget to like, subscribe, and hit the notification bell so you never miss a new lesson. And if you have any question or ideas for future tutorials, drop a comment below. See you in the next video. Hello friends, welcome back to another Python tutorial. Have you ever wondered how Python finds where your data lives inside a dictionary or a set so fast? The secret behind all that speed is a simple but powerful function called hash. In this video, we'll explore what hashing means, how hash works in Python, and where it's used in real programs. Part 1. What is a hash? In simple words, the hash function returns a unique integer that represents an object. That number helps Python store and retrieve data lightning fast. Example: I define a variable and assign it 42. Let's print it. Let's print hash x and run it and print 42. I define a variable and assign it Python and print hash text and print it and print hash. Each time you call hash on a value, Python gives you a numeric fingerprint of it. So here both 42 and Python have their own unique hash values. Part 2. Why hashing matters? Hashing is the foundation of data structures like sets and dictionaries in Python. Whenever you use a dictionary key, Python actually calculates its hash to decide where to store its value. Example: why hashing matters? I define a variable and assign it a dictionary. Print hash apple. Print data apple. Let's print it and print 10 and hash. Okay, part 3. Hashable objects. Not every object in Python is hashable. Only immutable objects, ones that don't change, can have a stable hash. That's why numbers, strings, and tuples are hashable, while lists and dictionaries aren't. Example: print hash 100. Let's print it and print 100. Let's print hash hello, hashable. Let's print hash 123 in tuple. Lists are not hashable. I define a variable and assign it a list. Let's print it. Output type error, unhashable type list. Okay, unhashable type list. Okay. Lists and dictionaries can change, so Python can't rely on their hash being the same letter. Part 4. Real use case. Duplicate detection in sets. Sets use hashing under the hood to automatically remove duplicates. Example: I define real use case duplicate detection in sets. I define a variable and assign it a dictionary. Let's print and print in for loop. Okay, let's print it and print 10, 20 and 30. Okay. Using those hash values, Python quickly recognizes that 10 already exists and avoids adding it again. Part 5. Custom hashing for your own classes. You can even define your own hash function for custom objects by implementing underscore underscore hash underscore underscore and underscore underscore eq underscore underscore. You tell Python how your object should behave in hash based collections. Example: custom hashing for your own classes. Excuse me. Self ID. Okay. Two students with the same ID. I define a variable and assign a student Ali and 101. I define a variable and assign it a student Reza 101. Print len students. Let's run it and print 1. Okay. Because both students share the same student ID underscore ID, our custom hash function treats them as equal. So only one of them is stored in the set. Part 6. Recap and takeaway. Let's review what we've learned today. Hash generates a unique number that represents an object. Immutable objects are hashable, like strings, numbers, tuples. Hashing pairs, Python, dictionaries, and sets. You can customize hashing in your own classes. If you enjoyed this lesson, hit that like button, subscribe for more Python magic, and comment below what topic you'd love to see next. Until next time, keep coding, keep learning, and enjoy Python. Hey coders, ever copied a variable in Python and got surprised when change one also changed the other? That's because not all copies are created equal. In this video, we'll break down the difference between value type and reference type and learn what shallow and deep copies really mean. Let's dive in. Part 1. Value type copy. Let's start with something basic. Example. I define a variable and assign it 42, and then I define a variable and assign it a, and a equal 99. Let's print a and b. Let's run it. A 99 and b 42. Okay. Here we have a assigned to a assigned to 42, then b equal a. After changing a to 99, b stays 42 because numbers are value types. Part 2. Reference type copy. Now let's try with a list which is a reference type. Example, change the list like this and print C and print D. Okay, let's run it. Look, changing the first element of C also changed D. That's because both C and D point to the same list in memory. Part 3. Shallow copy with copy.copy. To fix that, Python gives us the copy module. Example, shallow copy with copy.copy. Excuse me. Okay. Excuse me. Import copy. Then I define a variable and assign it a list. Define a variable and assign copy.copy scores. Change the list like this. Print scores and print backup scores. Let's run it. Now the issue is solved. Changing the original list no longer changes the copied one. But hold on, that's only true for one dimensional lists or shallow structure. Part 4. The shallow copy problem with nested list. Let's see what happens with a multi-level list. Example, part 4. I define a variable and assign it a nested list. Change the list like this and print matrix 1 and print matrix B. Okay, run it. Oops, the first row in matrix B also changed. That's because copy.copy only duplicates the other lists. The inner lists are still shared references. Part 5. Deep copy with copy.deepcopy. To fix that properly, we use copy.deepcopy. Example, deep copy with copy.deepcopy. I define a variable and assign nested list copy.deepcopy. Then change the list like this. Print matrix X, print matrix Y, and let's run it. Now everything works perfectly. Deep copy duplicates every level of the structure, so no inner reference are shared. Each list, sublist, object all have their own independent memory. Part 6. Quick summary. Recap. Numbers and strings value type stored separately. List, dict, sets, reference type, shared memory. Use copy.copy for shallow copy, only top level. Use copy.copy for deep copy, copies all levels. So, next time your variable mysteriously update themselves, you'll know why. If you enjoyed this tutorial, smash that like button, subscribe for more Python tips, and tell me in the comments what topic you want next. Until then, code smart, copy deep. Hi everyone. In this video, I'll show you why working with decimal numbers in Python isn't always as precise as you might think, and how to fix it using the decimal module. Step 1. The floating point problem. I define a variable and assign it 0.1. Then I define a variable and assign 0.2. Print a plus b. You might expect this to print 0.3, right? Let's run it. But look, it actually prints 0.3000004. So what's happening here? This is a classic floating point precision problem. Python lost most programming language represents decimal in binary floating point, and some numbers can't be stored exactly in that format. So small rounding errors appear. Step 2. The solution using decimal. Step 2. The solution using decimal. From decimal, import decimal. Then print decimal 0.1 as a string plus decimal 0.2 as a string. Let's run it and print 0.3. The result is exactly 0.3. No extra digits. The important thing to remember is when you use decimal, always pass the value as a string, not a float. For example, decimal 0.1 as a float would still give you the same floating point issue. Step 3. Controlling precision. Step 3. Controlling precision. I define a variable and assign decimal 1 as a string, division decimal 56 as a string. Print x. Let's run it. By default, the decimal context only shows a limited number of digits, 28 precision digits, as you can see. But if you want more decimal places, you can change the precision setting. Step 4. Setting global precision. Step 4. From decimal, import get context. From decimal, import context. Get context. Get context dot prec equal 80. Then print decimal 1 as a string, division decimal 56 as a decimal. Let's print it. Now Python will calculate the result with 80 digits of precision, as you can see. You can use this if you want globally higher precision across your code. Step 5. Local context temporary precision. From decimal, import local context. Then, with local context as ctx, then ctx.prec equal 100, print decimal 1 as a string, division decimal 56 as a decimal. Let's run it and print. Then okay, when you use local context, the precision change only applies inside the with block. Once you exit the block, the global precision returns normal, so it won't affect the rest of your program. Closing. And that's it. You now know how to make precise decimal calculations in Python using the decimal module. If you found this helpful, don't forget to like and subscribe for more Python tips. See you in the next video. Hello everyone, welcome to this Python tutorial. Today we are going to learn about logging in Python, which is a very useful tool for debugging and maintaining your applications. Instead of using print statements, logging allows us to record events with different severity levels, making our debugging process much more manageable. Section 2. Importing the library. First, let's import the logging module. It's built-in module in Python, so there's no need to install anything extra. Section 2. Importing. Import logging. Okay. By default, logging logs message at the warning level and above. Let's see how to set this up. Section 3. Configuring. Basic config. To customize the logging behavior, we use basic config. We can set the level, format, and even the output file. Section 3. Configuring basic config. Logging.basic config. Level and format. Okay. In this example, I'll set the log level to debug, which will display all message from this level and above. The message format includes the time, level, and the main log message. Section 4. Different log levels. Logging provides several severity levels: debug, info, warning, errors, and critical. Let's see example of each. Section 4. Different log levels. Debug, info, then warning, then error, then critical. Let's run it. Excuse me. Okay. Run it and print it. Debug info, warning, error, and critical. In larger file or complex applications, using this level helps you quickly find issue and receive the necessary notifications. Section 5. Logging to a file. You can also log messages to a file. Just specify the file path in the basic config. Okay. I comment it. Excuse me. Comment. Then here. Section 5. Logging the basic config. File name. Then level. Then format. Okay. Excuse me. Here. And copy paste. Then comment. Okay. Now, all messages will be saved in the app.log file. Run it. And here, app.log. Okay. Section 6. Practical example. Let's have a practical example that show how to manage potential errors using logging. Section 6. Practical example. Excuse me. Error. Result, then logging.info. In this example, if the user inputs 0, the division by 0 error is logged, but the program continues to run. Okay. Section 7. Conclusion and key. In this tutorial, we learn how to use logging in Python. The most important takeaway is to use logging for debugging and maintaining applications instead of print statements. Also, you can adjust the different levels to see various messages and save logs to a file. Closing and encouragement. I hope you found this video helpful. If you have any questions, please ask in the comments and don't forget to subscribe to the channel. Thank you. In Python, there are several built-in functions that work with iterable objects. An iterable is any object that can be looped through, such as litters, tuples, sets, and dictionaries. Let's start with a simple example. Suppose we have a list of temperature. Now, imagine we want to convert every temperature from Celsius to Fahrenheit. We can create a function for that. This function takes a Celsius value and returns its Fahrenheit equivalent. Instead of using a loop, we can use Python built-in map function like this. And let's print it. And let's run. And the output. The map function applies the given function to every item in the iterable and returns the transformed values. Let's make the output a little more informative. Suppose we want to keep both the original temperature and the converted value, like this. Now, apply it with map. Let's print and let's run it and the output. Okay. Notice that the result is now a list of tuples contain both values. The map function can also work with multiple iterables. Suppose we have two lists like this. We want to calculate the final price after applying each discount. Okay. And let's print. And let's run and output. Python takes the first item from each list, applies the function, then moves to the next pair, and so on. You can even use more than two iterables, like this. And let's print and let's run and output. The key rule is simple. If your function accepts one parameter, provide one iterable. If your function accepts two parameters, provide two iterables. If your function accepts three parameters, provide three iterables. The map function is a powerful tool for transforming data efficiently and can often make your code cleaner and easier to read than traditional loops. Subscribe for more Python tips. So far, we've seen how maps can transform data. But what if we don't want to transform items? What if we only want to keep certain items and remove the rest? That's exactly where the filter function comes in. Let's say we have a list of numbers. Imagine we only want to keep the odd numbers. To do that, we need a condition that tells Python whether each value should stay or be removed. The filter function takes two arguments. A function that returns either true or false, an iterable such as a list, tuple, or set. Here's an example. Let's run. Why does this work? When a number is odd, n%2 returns 1, which Python treats as true. When a number is even, n%2 returns 0, which Python treats as false. As a result, only odd numbers remain. What if we want to the even number instead? We can reverse the condition like this. And let's run. This time numbers divisible by 2 pass the test and stay in the result. Let's try a different condition. Suppose we want all numbers that are not divisible by 2, like this. Let's run. Since multiples of 3 produce a remainder of 0, they are excluded. There's another useful feature of filter. If you pass none as the first argument, Python automatically removes value that evaluate to false. For example, and let's print and let's run. All false values such as 0, empty string none, and false are removed automatically. The key idea is simple. Use map when you want to transform data. Use filter when you want to select data based on a condition. Subscribe for more Python tips. In Python, sometimes we need to reverse the order of elements in a sequence. For example, taking a list and reading it from the last element to the first. Instead of manually looping or creating a new structure, Python provides a built-in tool called reverse functionality through reverse. Basic example. Let's start with a simple list. To reverse this sequence, we can use the reverse function. And let's print. And let's run. Important concept. It returns an iterator. One of the most important things to understand is that reverse does not return a new list. Instead, it returns a reverse iterator, like this. Let's print. This will show something like. Let's run and print. To actually see the values, you need to convert it into a list or loop through it. Memory efficient behavior. Unlike creating a reversed copy of the list, reverse does not duplicate the data in memory. It simply reads the original list from the end to the beginning. This makes it very efficient, especially when working with large datasets. For example, if you have a very large list, reverse it with reversed. will not significantly increase memory usage. But if you convert it into a list like this, then Python creates a new list in memory, which duplicates the data. Using reversed in a loop, you don't even need to convert it to a list. You can directly loop over it, like this. And let's run. And let's print. Key idea. Reverse return an iterator, not a list. It does not modify the original data. It is memory efficient. You can convert it to a list if needed. You can use it directly in loops. Final thought. Functions like map, filter, and reversed are all iterator-based tools in Python. They are designed to be fast, memory efficient, and scalable, especially when working with large amounts of data. Understanding this concept is a key step toward writing more professional Python code. Subscribe for more Python tips. Imagine you have a list of numbers and you want to arrange them from smallest to largest. Let's create a sample list. Python provides a built-in function called sorted that makes this incredibly easy, like this. And let's run, and let's print. The original list remains unchanged because sorted creates a new sorted list, like this. And let's print, and print it. So remember, sorted returns a new list. The original list stays exactly the same, sorting in descending order. Sometimes we need the largest value first. We can use the reverse parameter, like this. Okay, and let's run, and let's print it. By default, reverse is false, which means ascending order. When it's set to true, Python sorts in descending order. Custom sorting with key. Now, let's do something more interesting. Suppose we don't care about the actual numbers. Instead, we want to sort them according to their distance from 0. In mathematics, that's called the absolute value. For example, ABS minus 15, let's run, 15, and ABS 15, let's run, 15, also 15. Let's sort our list based on absolute value, like this. And let's run and sort it. Notice that Python is not sorting by the actual number anymore. It is sorting according to the value returned by ABS. This is exactly what the key parameter does. The key function transforms each element before comparison, creating our own key function. We are not a built-in function. Let's create our own function. Now, we can use it as a sorting key, like this. And let's print, and let's run, and let's print. Because negative cubes remains negative, this creates a different ordering strategy. The important idea is that Python compares the values produced by the key function using lambda function. Instead of defining a separate function, we can use a lambda expression. For example, and let's run, and let's print. Here Python sorts according to the square of each number. Lambda functions are very popular because they allow us to define a small custom sorting rules directly inside the sorts called multi-level sorting. Now, let's look at more advanced example. Suppose we have value like this. Our goal is even numbers first, odd numbers second. Numbers within each group sorted from smallest to largest. We can achieve this using a tuple like this. And let's run, and let's print. Let's understand what's happening. For each number, Python creates a tuple. For example, like this, and like this, and like this. The first value determines whether the number is even or odd. The second value determines the order inside that group. Python first compares the first element of the tuple. If two elements have the same first value, it compares the second elements. This is called multi-level sorting. Real-world example. Imagine we have employee records like this. Excuse me, like this. Okay, let's sort them by salary first and age second. Let's sort it, and let's run and sort it. Here, emp2 is salary, emp1 is age. Python will first compare salaries. If salaries are equal, it will compare ages. This technique is extremely common in data analysis, backend development, and database applications. Subscribe for more Python tips. When working with Python, you'll often need to loop through the items of an iterable object. A simple example is iterating through the character of a string. Let's start with the following text. If we want to process each character one by one, we can use a basic for loop like this. And let's run. And let's print it. For every character, this code prints the original character its uppercase version, its lowercase version. While this example isn't particularly practical, it demonstrates how easy it is to access and manipulate each element during iteration. Now imagine that we also need to know the position of each character inside the string. One approach is to work with indexes directly, like this. Let's run and let's print it. Excuse me. Let's print it. Okay. This works perfectly fine, but Python provides a cleaner and more readable solution: the enumerate function. With enumerate, we can access both the index and the value at the same time, like this. And let's print. And let's run. And let's print it. Okay. The output will look something like. Under the hood, enumerate generates pairs containing an index and its corresponding value. That's why we can unpack the result directly into two variables inside the loop. If we are curious about what enumerate actually produces, you can convert it into a list, like this. And let's print. And let's print it. One important thing to understand is that enumerate doesn't create the entire sequence in memory right away. Instead, it returns an iterator that generates value only when needed. This makes it efficient, especially when working with large datasets. As a general rule, whenever you need both the position and the value of an item during iteration, enumerate is usually the most Pythonic and readable solution. Subscribe for more Python tips. Hello everyone, in today's lesson we are going to explore Python function that helps us combine related pieces of data. Let's imagine we have two lists. The first list contains a student name, like this. And the second list contains their exam scores, like this. A common goal is to process both lists together. One approach is to use indexes, like this. And let's print. And let's run. Okay, this works. But Python gives us a more expressive solution. That's where zip comes in, like this. And let's print. And let's run. And let's print it. The idea is simple. Zip takes the first item from each iterable and groups them together. Then it takes the second item from each iterable and so on. You can think of it as creating pairs of related information. Let's inspect what zip produces, like this. and let's print, and let's run and print it. Notice that every pair is stored as a tuple. This makes it easy to loop through the data later. Now, let's add another score. What happens? And let's print, and let's run and print. Python stops when the shorter iterable ends. Since there are only 4 students, only 4 pairs are produced. 1, 2, 3, 4. This behavior prevents index errors and keeps iteration safe. We are not limited to 2 iterables. Suppose we also have a student A's, like this. Now, we can combine all 3 collections. And let's print, and let's run and output. The same rule applies. Iteration stops at the shortest iterable. Imagine we already have paired data like this. What if we want separate collections again? Python lets us do that using unpacking, like this. And now print names and marks. And let's run and print. This technique is often called unpacking or unzipping. You'll frequently see zip when 1. Matching names with IDs. 2. Combining products with prices. 3. Pairing dates with sales figures. 4. Processing multiple datasets together. Whenever 2 or more collections represent related information, zip is usually worth considering. Summary: the zip function 1. Combines multiple iterable elements by element. 2. Produce tuples. 3. Stops at the shortest iterable. 4. Works with 2 or more collections. 5. Can be reversed using unpacking with a star. Mastering zip will help you write cleaner and more Pythonic code. Subscribe for more Python tips. Thanks for watching, and see you in the next lesson. Most Python developers use for loops every day, but many don't know what's happening behind the scenes. Let's start with a simple example. And let's run. And this prints each character one by one. What actually happens is that Python creates something called an iterator and keeps asking it for the next value until there are no values left. We can create that iterator ourselves, like this. Let's print, and let's print, and let's run, and let's print it. Okay, Every time we call next, the iterator moves forward. Let's continue. And let's run. Stop iteration. That simply means there are no more values available. To avoid the error, we can provide the default value like this. And print. And print. This code is comment. Okay. And let's run. The last call returns our default value instead of raising an exception. Now, let's look at another interesting example. Iterators don't have to come from strings or lists. We can create an iterator that repeatedly calls a function like this. Return and let's print and let's run and print it. Python keeps calling the function until it returns 5. This is a powerful pattern for processing streams of data. Now, let's learn a cool iterator trick. Suppose we have a sequence of numbers like this. Okay. And we want to group them into chunk of 3. Let's print and let's run and print it. Okay. Why does this work? Because all 3 arguments passed to zip are actually the same iterator. Every time zip requests values, the iterator advances. So the first tuple gets the first 3 numbers. The second tuple gets the next 3 numbers, and so on. In modern Python, we can make these safer like this. And print. And let's run and print it. With a strict equal true, Python raises an error if the data can't be evenly divided into groups. For example, this produces an exception because 10 items can't be perfectly split into groups of 3, and that's the key idea. A for loops is just a convenient interface over iterators. When you understand either and next, you gain much more control over how data is processed in Python. Subscribe for more Python tips. Hello everyone! In this lesson, we're going to learn 2 super useful Python features, range and slicing. You'll see these everywhere in real-world Python code, from loops to data processing and even machine learning projects. Let's start with range. The range function generates a sequence of numbers. Simple example. Notice something important. Python starts from 0 by default and the ending value is not included. So range 5 means start at 0 and stop before 5. You can also specify where the sequence starts. Again, 8 is not included. Think of it as start from 2 and keep going until you reach 8, but don't actually take 8. The third argument controls the step size. Here Python jumps by 3 each time. Range can also move in reverse using a negative step. The sequence moves backward and decreases by 2 on each step. Now, let's talk about slicing. Slicing allows us to extract part of a string, list, tuple, or other sequence. Let's use a string. This means start from indexed 6 and continue until the end. Remember, indexes start at 0. The first number is where we start. The second number is where we stop. Just like range, the stop position is excluded. Slicing also supports steps. Python takes every second character. A really popular trick the negative step tells Python to move backward through the string. Python even provides a built-in slice function. The advantage is that the slice can be stored in a variable and reused throughout your code. For large applications, this can make your code cleaner and easier to maintain. Summary. Let's review. 1. Range creates sequence of numbers. 2. The stop value is excluded. 3. A step value controls how numbers change. 4. Negative steps allow reverse counting. 5. Slicing extracts portions of strings and lists. 6. Slice support start, stop, and step value. 7. Slice lets you create reusable slicing rules. Mastering these two concepts will make working with Python data structures much easier. Subscribe for more Python tips. In today's Python lesson, we're going to explore a very useful data structure called NamedTuple. Before we get there, we'll quickly review the most common built-in containers in Python and see where NamedTuple fits among them. By the end of this video, you'll understand lists, tuples, sets, dictionaries, why NamedTuple exists, when to use it, how to customize behavior. Let's get started. Section 1. Common Python containers. Python provides several built-in ways to store data. Let's start with a list. Let's print. Okay. Lists preserve order and allow duplicate values. Now let's compare that with a set. Sets automatically remove duplicates. They are useful when uniqueness matters more than ordering. Next, let's look at tuples. A tuple looks similar to a list, but there's a major difference. Tuples are immutable. For example, this raises an error because tuple values cannot be modified after creating. Okay. Section 2, dictionaries. Sometimes the data has meaning attached to each value. Imagine we are storing information about a city. And okay. Dictionaries make data easy to understand because each value has a descriptive key. However, dictionaries are mutable. This modification is allowed. Section 3. The problem. Let's imagine we are storing information about a point on a map. We could use a tuple. But what does each position mean? You have to remember, index 0 equal x, index 1 equal y, index 2 equal label. This becomes difficult in large projects. Dictionaries solve readability. But dictionaries are mutable. What if we want both readable names, immutability? This is exactly why name tuple exists. Section 4. Introducing name tuple. Python collections module provides name tuple. Okay. Let's define one. Now we have a completely new type. Section 5. Creating object. Let's create an instance. Notice how readable this is. Section 6. Accessing values. Instead of numeric indexes, we use attribute names. This is much easier to understand than. Section 7. Immutability. Name tuple objects are immutable. Let's try modifying one. Python raises an error. This protects the data from accidental changes. Section 8. Creating updated copies. Although we cannot modify an existing object, we can create a new one. Okay. The original object remains unchanged. Section 9. Converting to dictionary. Name tuple can easily become a dictionary. This is useful when working with APIs or JSON data. Section 10. Extending name tuple with methods. We can create a more powerful version by inheriting from it. Let's build a 2D point. Now create a subclass. Okay. Create 2 points. Now, the plus operator works naturally. Conclusion. Today we learn lists are ordered and mutable. Sets store unique values. Tuples are immutable. Dictionary provide name field. Name tuple combines readability and with immutability. We can access values using attributes. We can create update copies with replace. We can even extend name tuple with custom methods. Name tuple is an excellent choice when your data should remain unchanged while still being easy to read and maintain. Subscribe for more Python tips. Thanks for watching, and I'll see you in the next Python tutorial. In the previous lesson, we learned about name tuple from the collections module. It gives names to tuple element, making code much easier to read. Python also provides a newer and cleaner approach. Name tuple from the typing module. Instead of creating a tuple with a function, we define a class. Now, we can create object in different way. All of these are valid because fields can be passed by position or by name. One advantage is the type hints. They don't change how Python runs your code, but they make the code easier to understand and help others provide better suggestions. You can access values using field names. Or just like a normal tuple. Since it's still a tuple underneath both style work. NameTuple also includes several useful methods. You can see the field names, or create a modified copy. Notice that the original object never changed. This raises an error because NameTuple is immutable. Excuse me. Sometimes you want something that behaves like a structure instead of an immutable tuple. A lightweight option is the ypstruct package. Install it. Okay? Then create a structure like this. You can read values. And you can also modify them. You can even convert it to a dictionary. A useful trick is creating a template object. Then duplicate it whenever you need a fresh object. Okay? Each element is an independent object, so change one won't affect the others. Summary. NameTuple is the classic approach. NameTuple is cleaner and supports type hints. Both are immutable. If you need mutable structures without writing a full class, libraries like ypstruct can be a convenient alternative. Subscribe for more Python tips. Today we're going to master one of the most useful tools inside the collections module, counter. By the end of this video, you'll know how to count anything with just a few lines of Python. Import counter. Counter behaves like a dictionary, but instead of storing arbitrary values, it automatically counts how many times each item appears. Let's see it in action. Die simulation. Instead of entering numbers manually, let's simulate rolling a die. Now, counting every number manually would be painful. Instead, Python counted everything for us. Access count. Notice something interesting. Even though 10 never appeared, counter returned 0 instead of raising an error. Most common items. Want to know the winner? Or maybe only the top 3. This is incredibly useful for data analysis. Update existing counter. Imagine new data arrives. Instead of rebuilding everything, counter simply update the counts. Total elements. This tells us how many observations we've counted overall. Rebuild the original data. Counter can recreate all elements. Very useful for testing and debugging. Create counter from dictionary. You don't always need a list. Mathematical operations. Let's compare two stores. Addition. Intersection. Union. Difference. Counter supports these operations natively, making it surprisingly powerful for inventory systems and data comparison. Mini project. Analyze paragraph. And let's begin. This tiny program is actually the foundation of many natural language processing techniques. Now, it's your turn. Download any article from the internet, count every word, remove punctuation, convert everything to lowercase, then display the 5 most common words. If you can build that project, you've officially mastered Python counter. Subscribe for more Python tips. In this lesson, we're going to learn about a very useful data structure called defaultdict from Python collections module. If you've ever worked with dictionary, you've probably seen a key error when trying to access a key that doesn't exist. Let's start with a regular dictionary. This works perfectly because the key already exists. But what happens if we try to access another key? Python raises a key error because horse is not in the dictionary. This behavior is completely normal, but sometimes we actually want missing key to return a default value instead of causing an error. That's exactly why defaultdict exists. First, import it from the collections module. Okay. Now, let's create a dictionary that automatically returns 0 whenever a new key is accessed. Everything looks similar to a normal dictionary. Now, let's check an existing key. Okay, print it. Now, let's access key that has never been created. Instead of raising an error, the output is simply 0. Why? Because int creates the default value and int returns 0. The function you pass to defaultdict is called the default factory. Different factories create different default values. For example, since the default value is an empty list, you can immediately append items without checking whether the key already exists. You can also use a set. Because sets store unique values, duplicates are automatically ignored. One of the most common use of defaultdict is counting items. Imagine we have a list of fruits. Using a regular dictionary, we would have to check whether each key already exists. Okay. Notice how we never needed to write an if statement. The dictionary automatically created each missing key with the value 0, then increased it. This makes the code shorter, cleaner, and easier to read. As a practice exercise, try building your own word frequency counter using defaultdict. Compare it with the version that use a regular dictionary and notice how much simpler the code becomes. Subscribe for more Python tips. So far, we have been using Python regular dictionaries. In newer version of Python, dictionaries generally preserve the insertion order of keys. However, if you want to program mathematically, change that order. A normal dictionary has limited capabilities. Let's assume we have a list of tasks. Now, if we decide that the item coding should be moved to the end of the list, there is no direct way to do that using a standard dictionary. This is where OrderedDict comes into play. First, we import it from the collections module. Now, we place the same data inside an OrderedDict. Okay. One of the interesting features of OrderedDict is the move to end method. For example, if we want to move meeting to the end of the dictionary, okay? And if we want to move a key to the beginning of the dictionary, we simply pass last equal false. And print it. Another useful method is popetem. This method removes and returns the last item. If we want to remove the first item instead, we use last equal false. Okay, we can also remove a specific key, just like a normal dictionary. So, OrderedDict has almost all the capability of a regular dictionary, but it also provides extra tools for managing the order of items. If order matters in your project, such as processing sequence, workflow, or data handling, then OrderedDict can be a great choice, giving you more control compared to a standard dictionary. Subscribe for more Python tips. When you're learning dictionary in Python, you usually think of them as standalone collections of key-value pairs. But in real applications, data often comes from multiple places. Imagine you're developing a video game. There are 3 levels of settings. First, the game has default settings that every player starts with. Then each gaming team can customize some of those settings. Finally, every individual player can have their own preferences. The interesting part is that not every setting needs to be defined at every level. For example, suppose the game's default configuration look like this. Now, imagine a specific team prefers a harder game and disables the background music. Okay. One player on that team decides to change only their display resolution. Now, here's the question. If we want to know this player preferred language, where should Python look? It's not inside the player settings. It's also not inside the team's settings. Eventually, it should fall back to the default configuration. Doing this manually isn't difficult for one or two dictionaries, but imagine 5 or 6 configuration layers. You'd have to write something like that quickly becomes repetitive and hard to maintain. Fortunately, Python already provides a cleaner solution. The ChainMap class combines multiple dictionaries into a single view. Okay. The order matters. Python first checks the player's settings. If the key doesn't exist there, it looks in the team's settings. If it's still missing, it checks the defaults. Let's test it. The player's own preference overrides everything else. Now, let's check the difficulty. The player didn't define it, so Python finds it in the team's configuration. Finally, let's request the language. Neither the player nor the team customized that value, so Python automatically falls back to the default dictionary. This fallback behavior is exactly what makes ChainMap so useful. Another nice feature is that if you add a new value to the ChainMap, it is written only to the first dictionary. The theme and default dictionaries remain unchanged. ChainMap also keeps reference to all of the dictionaries it manages. You can inspect them with okay. This returns the list of dictionaries in the order Python searches through them. In real-world projects, ChainMap is especially useful when working with layered configurations. For example, application defaults, configuration file, environment variables, command line arguments, user preferences. Instead of writing complex fallback logic yourself, ChainMap handles the lookup automatically. It's a simple tool, but it can make configuration management much cleaner and easier to maintain, especially as your application grows. Subscribe for more Python tips. One of the most useful data structure available in Python's collections module is deque, which stands for double-ended queue. Unlike a regular queue that is typically processed from one end, a deque allows you to efficiently insert and remove elements from both the front and the back. Let's import it first. A deque can be created from any iterable such as a list, tuple, a string, or even a generator. Okay. Appending an item to the end of a Python list is usually fast, but inserting or removing elements at the beginning requires shifting many elements. With deque, both ends are optimized. Append to the right, O1, append to the left, O1, pop from the right, O1, pop from the left, O1. This makes deque an excellent choice for queues, sliding, windows, buffering systems, scheduling algorithms, and many real-time applications. Adding an element to the right. Added. Okay. Remove the last item. Excuse me. Adding an element to the left. Adding an element to the left and add to the left. Okay. Removing the last item. Excuse me. Okay. Let's run and remove last item. Remove the first item. Okay, first item is removed. Instead of adding one item at a time, you can append several values together. Extend from the right. Okay. Extend from the left. Okay. Notice something interesting. Although the values were supplied in the order 30, 31, 32, they appear in reverse order. That's because each element is inserted one at a time at the front. you can reverse all elements in place. Okay, it's reversed. The original object is modified directly. One of the most unique features of deque is rotation. Rotate the right. Okay. Rotate the left by using a negative value. Excuse me, rotate the left and rotate to the left by using a negative value. This here. And rotate negative. Rotate the left by using a negative value. Rotation is particularly useful in simulations, cyclic buffers, scheduling algorithms, and game logic. Suppose we have letters. Find the first occurrence. The output is 0. Start searching from a specific position. Three. Search inside a range. Three. Okay. If the value cannot be found inside the specified range, Python raises a value error. Count how many times an element appears. The output is 3. Insert an element before a given index. Okay. Remove the first matching element. Or remove the first A. Excuse me. Okay. Okay. Only the first matching element is deleted. The deque class offers much more than a traditional queue. Besides fast insertions and deletions at both ends, it also supports rotations, efficient searching, counting, insertion at arbitrary positions, and removal by value. Whenever your applications frequently modify both the beginning and the end of a sequence, deque is usually a better fit than a standard Python list. Knowing when to use it can make your program cleaner, faster, and easier to maintain. Subscribe for more Python tips. One of the interesting characteristics of Python is that it doesn't enforce data type as strictly as languages like C or C++. Python is dynamically typed, which means the actual type checking mostly happens while the program is running rather than before execution. For example, let's create a normal Python list. Later in program, you can completely change the type of one of the elements. Okay, Python allows this because a list can store different kinds of objects at the same time. In C or C++, this wouldn't be possible with a regular array. Once the array is declared to hold integers, every element must be an integer. Python lists are flexible, which is great for many situations. However, sometimes that flexibility isn't what you want. If you're working with thousands of numeric values, you may prefer a container that only accepts one specific data type. That's where the array module becomes useful. First, import the array class. Okay. When creating an array, the first argument is a type code which tells Python what kind of values the array should store. For example, the type code I represents signed integers. Okay. Now, let's insert some integers values. Okay. Accessing elements work exactly like a list. Okay. Now, let's see what happens if we try to insert a floating point number. Python immediately raises an error because this array is designed to store integers only. The same happens if we try to assign a string. Okay. Again, Python rejects the assignment because the value doesn't match the array's data type. You can also add multiple elements at once using extend. Okay, let's print. Another option is to initialize the array with values from the beginning. Okay, print. Excuse me. Both approaches create exactly the same type of object. The same important point is that once the array is created with a specific type code, every element must follow that type. Arrays are especially useful when you're working with large collections of numbers, since every element has the same data type. Memory usage is more predictable, and the data structure is more compact than a regular Python list. For general purpose programming, Python lists are usually the preferred choice because of their flexibility, but when you need homogeneous data and more efficient storage, the array module is a better fit. Subscribe for more Python tips. Suppose you have a dictionary that other parts of your program need to read, but you don't want them to modify it. Here's an example. Okay. Reading values works exactly like a normal dictionary. Now, let's see what happens if we try to update it. Python raises a type error because a mapping proxy type object is read-only. But here's the interesting part. The proxy itself can't be modified, yet it still stays synchronized with the original dictionary. Okay. Even though we never touched the proxy, it immediately reflects the latest changes. That's because mapping proxy type doesn't create a copy of the dictionary. Instead, it provides a live, read-only view of the original object. So, the owner of the original dictionary can continue making update, while everyone else gets safe read-only access. This is especially useful when you want to expose configuration data, look up tables, or shared application state without allowing accidental modifications. Subscribe for more. See you in the next video. Hi everyone. Today we're talking about one of Python's coolest and most powerful features, comprehensions. If you want to write cleaner, faster, and more elegant code, this is your secret weapon. In Python, you can use comprehensions to create lists, sets, and dictionary in just a single line of code. Let's see how it works. Let's start with a list comprehensions. The basic formula is simple. You put an expression followed by a for loop inside the square brackets. For example, let's say we have a list of fruits and we want to create a new list containing the length of each fruit's name. Here is how easily we can do it. Let's print. Okay. Super clean, right? But what if we only want to calculate these 4 fruits that have more than 4 letters? We can simply add an if statement at the very end. Look at this. Okay. We can use the exact same logic to create sets and dictionary using curly brackets. Remember, a set automatically removes duplicate values. Let's say we have a list of names with some duplicates and we want to convert them all to uppercase while removing their repeats. Okay. Now, what if we want to dictionary instead? Let's map each unique name to its character count. We just need to provide a key value pair inside the comprehensions, like this. Okay. Comprehensions are incredibly powerful, but here is a pro tip. Don't overdo it. If your comprehension gets too long or complicated, it's destroy readability. Keep it simple. Once you get used to writing Pythonic code like this, it becomes a habit. Just like driving a luxury sports car. You won't ever want to go back to regular loops. If you found this useful, hit that like button and subscribe for more quick Python tips. See you in the next one. Hi everyone! In our previous videos, we looked at how list, set, and dictionary comprehensions work in Python. They are fantastic for creating collections on the fly. For example, if we want a list of square numbers from 0 to 9, we can easily write it like this inside square brackets. But what happens if we simply change those square brackets to parentheses? You might intuitively expect Python to create a tuple comprehension, right? Let's try it out and print the result. Okay. Surprise! It's not a tuple. Python gives us a generator object. But what exactly is generator? And why should you care? Let's dive deeper into how it manages memory. To understand generators, let's look at a massive dataset. Imagine we want to square 1 million numbers. If we use a list comprehension, Python calculates all 1 million square immediately and stores them directly in your computer RAM. Okay. Let's run and this completely occupies your memory. If you have billion of items or limited RAM, your program might crash. Now, let's see what happens when we use a generator expression instead. Look at that. The generator takes up almost zero memory, just a few bytes. Why? Because it hasn't actually generated any numbers yet. It holds the potential to create them. It calculates each number on demand, one at a time, only when you ask for it. So, how do we get the data out of generator? The most common way is using a for loop. The loop automatically calls the built-in next function under the hood, pulling one item at a time until the generator is exhausted. Okay. Generators work beautifully with Python built-in reduction functions like max, min, and sum. Let's say we have a list of random values, both positive and negative, and we want to find the maximum of their absolute values. Okay. While this works, it creates an intermediate list in memory. We can optimize by dropping the square brackets entirely and passing the generator expression directly into the function. Python allows us to omit the inner parentheses for a cleaner look. Okay. Functions like max and sum are optimized to process iterators sequentially. Instead of building a whole list in memory and then finding the maximum, the generator feeds them one value at a time, keeping your application fast and memory efficient. To wrap up, whenever you need to process a large stream of data or pass items to a function that loops through them, always prefer generator expression over list. They boost performance and keep your memory footprint low. Just remember a golden rule of clean code: don't overnest your comprehensions, keep them readable. This particular type is called a generator expression. If you found this video helpful, please hit that like button, subscribe for more Python content, and I'll see you in the next one. Hey everyone, welcome back to the channel. Today we are diving into one of Python's most powerful built-in libraries for writing clean, memory-efficient code, itertools. If you've ever needed to create custom looping behaviors without burning through your system's RAM, this toolset is your best friend. In this video, we'll focus specifically on infinite iterators, loops that can run forever unless we tell them to stop. We'll cover three essential tools: count, cycle, and repeat. Let's get into the code. Number 1. The count iterator. First up is count. Don't confuse this with the counter class from the collections module. This is an infinite step counter. It takes a starting number and a step value, then increments infinitely. Let's say we want to generate unique IDs for a dynamic list of users, starting from 100 and skipping by 5. Okay. Okay. As you can see, using next fetches the next value on demand. If you use this inside a standard for loop, just make sure to add a break condition, or your script will run forever. Number 2, the cycle iterator. Next is cycle. This one takes an iterable, like a list or a string, and loops through its items continuously in a round robin fashion. When it reaches the end, starts right back at the beginning. A great real-world use case for this alternating UI theme, colors, or managing a rotation of worker shifts. Okay. Okay. The ensure your data cycles perfectly without your having to write manual index resetting logic. If index higher than len, it's fully automated and incredibly clean. Number 3, combining infinite iterators with zip. Now, here is where the magic happens. You might ask, if these run forever, won't they crash my program? Not if you pair them with zip. Python zip stops as soon as the shortest iterable is exhausted. Let's combine cycle with a finite list of tasks to create a schedule. Okay, let's run and output. Even though employees is infinite, the loop stops smoothly after 5 tasks because zip cuts it off. This is a brilliant way to map repeating patterns to finite dataset. Number 4, the repeat iterator. Finally, we have repeat. This returns the exact same element over and over again. You can either let it run infinitely or pass a second argument to limit the count. This is super useful when a function expects an iterable, but you just want to feed it a constant value. Okay. If you don't pass the times argument, calling the next repeat 10 will give you 10 forever. It acts as a lazy, constant data stream that takes up almost zero memory. And that wraps up our look at infinite iterators in Python. We covered count for sequencing, cycle for round-robin rotations, and repeat for constant data streams. Okay, if you found this video helpful, smash that like button, subscribe for more advanced Python content, and drop a comment below letting me know how you plan to use itertools in your projects. See you in the next one. Hey everyone! Today we're pairing Python lists using zip. It locks elements from multiple lists together into tuples. Let's look at the code. Okay. The output is 1 online, 2 offline, 3 busy. The standard zip stops as soon as the shortest list ends, dropping the remaining data from longer list. But what if you're working with time series or financial data and can't afford to lose any datasets? To keep going until the longest list is finished, use zip underscore longest from the itertools module. Okay, now look at the output. Python automatically fills the missing gaps with none. However, none values can crash your formulas. To fix this, you can set a custom placeholder using the fill value parameter. Okay, perfect. Now we get unknown instead of none. This is a lifesaver for handling asymmetrical dataset safely. If this helped, smash that like button and subscribe. Happy coding! Hey everyone, today let's look at itertools.accumulate. It's the perfect one-line tool for running totals or cumulative operations in Python without using messy loops. Imagine you want a running total of a list instead of a for loop. We can just pass the list to accumulate. And output is like this. Let's run. And it returns an iterator, convert it to a list, and you get the sequential totals: 10, then 30, then 60, and so on. If you have a starting baseline, use the initial parameter. The output will start with this value and have one extra element, like this. The output like this. And run. Okay. By default, it adds numbers, but you can pass a custom function like a lambda expression to do things like cumulative multiplication, like this. Okay, output like this. This easily creates factorials. And yes, you can combine this with an initial value 2 to scale the whole operation from a base number. So let's put like this. Okay. Great for math, finance, or recursive logic. If this helped, drop a like, subscribe, and tell me in the comment how you'll see it. See you next time. Hello everyone. Ever needed to iterate through multiple lists back to back, ending up with repetitive for loops like this? It's messy and redundant. Okay. Duplicating logic is bad practice, and combine this with the plus operator wastes memory. The professional way is using itertools.chain. It links your collection seamlessly with zero memory overhead. Excuse me. And let's spin it. Okay. These tools snap together like Lego bricks. You can even pass dynamic sequence like the repeat function straight into chain. Check this out. Okay. Now, what if you have a nested list of uneven sublists and you want to flatten it into a single sequence? We have two fast ways to do this. Method 1, use Python argument unpacking with the star operator. Let's run like this. Okay. Method 2 is even cleaner and more memory efficient. We use the dedicate chain.from_iterable method directly on the nested collection. Okay. And that's how you write cleaner, faster Python using chain. If this quick tip helped you out, hit that like button, subscribe for more, and drop a comment below. See you in the next one. Hey everyone, today we're covering 4 powerful tools from Python itertools module to supercharge how you filter data. Filter files, compress, drop file, and take file. Let's code. Number 1, filter files. We all know the standard filter, which keeps elements that meet a condition. the output like this. Let's run. Okay. Filter false does the exact opposite. It keeps elements where the condition is false, saving you from writing messy negative logic. Okay. The output like this. Number 2, compress. Compress filter a list using a parallel list of Boolean flags or masks. 1 or true keeps the item, 0 or false drops it. The output like this. As you can see, excuse me, you can easily pair this with the random module to create dynamic randomized selections. Excuse me. Okay, let's run and print. Number 3, drop wire and take wire. Finally, these two functions filter data based on sequential order, stopping the moment a condition changes. Drop wire deletes elements as long as the condition is true. Once it hits the first false value, it stops dropping and keeps everything else. The output like this. Okay, let's run. As you can see, take wire does the opposite. It keeps elements as long as the condition is true and completely shuts down at the first false value. Let's print. Output like this and run. As you can see, they are perfect complements, splitting your data right at the threshold boundary. And that's it for clean, fast ways to process sequential data in Python. If this helped, hit like, subscribe, and I'll see you in the next one. Hello everyone. Need to access the next or previous element inside a Python loop. It's crucial for time series, calculating difference, or moving averages. Let's see how to do it elegantly. The modern way. Let's run. Okay. Python itertools.reduce creates a moving window of size 2. It automatically pairs adjacent elements without any index out of bounds error. Unpacking in a for loop. Okay, let's run and print. Just unpack the tuples directly in your loop. Now you have access to both the current and the next values simultaneously. The classic way. Okay. No imports. No problem. Use zip with list slicing. We zip the list with itself. Shifted by 1. Larger windows. Let's run. Pairwise is limited or pairs, but with zip you can easily scale to 3, 4 or more elements to build any sliding window you need. Understand these pure Python tricks help you write cleaner code and grasp what libraries like pandas do under the hood. Like and subscribe for more Python tips. Hey everyone! Today we're looking at a clean way to process collections of data in Python using StarMap from the itertools module. Let's get straight into the code. The list comprehension approach. Imagine you have a list of tuples containing the width and height of different rectangles, and you want to calculate the area for each. And print the output like this. Okay, run. As you can see, this works great. We can even shorten it by using the asterisk operator to unpack the tuples automatically. Let's print and let's run. Okay, the StarMap alternative, but Python has a built-in tool designed extractly for this pattern. It's called StarMap. Here is how it works. Let's print and output like this. Okay, as you can see. As you can see, a star map automatically unpacks each tuple and passes the item as argument into our calculate area function. Why use a star map instead of a list comprehension? 1. Memory efficiency. A star map evaluates items lazily one by one, which is perfect for large datasets. Number 2. Cleaner code. It removes the need for extra loop variable, making your code look much more professional. If you found this quick tip helpful, drop a like and subscribe for more Python videos. See you in the next one. Hello everyone. Today we're looking at how to ditch nested for loops and cleanly generate all possible combinations using product from Python itertools module. The problem: the nested loop nightmare. Imagine pairing a cafe menu of drinks and cakes. The traditional way requires nesting multiple loops like this. Let's print. Okay, let's run and print. If you add a third option like cup size, you have to add a third nested loop, making the code messy and hard to read. The solution: using product. The product function solves this perfectly. No matter how many lists you have, your code stays clean with just one single loop. Excuse me. And let's print. Okay, let's run and print. Unlike zip, which pairs element one to one, product intersects every single element from all lists to ensure absolutely no combination is missed. The repeat parameter. If you need to multiply a list by itself, for example, simulation flipping a coin 3 times, use the repeat keyword instead of duplicating the list name. Okay, let's print and print. Okay. Whenever you need to generate all possible structural combination, the Cartesian product across multiple datasets, skip the nested loop, use itertools.product to keep your code readable, professional, and optimized. Subscribe for more Python tips. Hello everyone. In this lesson, I explain combination and a permutation. Number 1, combination. Order does not matter. Used when only the selection of items matters, and the argument doesn't create a new case. The second argument is required. and let's print. Let's run. Okay, let's print it like this. Number 2, permutation. Order matters. Used when the sequence or argument of item is critical. The second argument is optional. If omitted, it defaults to the full length of the input, like this. First, import libraries. Okay. And let's print. Let's run. Let's print it like this. Number 3, combinations with replacement. Duplicates allowed. Similar to combinations, but individual elements can be repeated more than once. Simulating dice rolls or DNA sequencing. With this function, the specified length can even be greater than the length of the input list. First, import library. Okay. Then print. Let's run and print it like this. Okay. All of these itertools functions return memory efficient iterators written in highly optimized C, making them incredibly fast and lightweight compared to custom nested loop. Subscribe for more Python tips. What's up everyone? Today we're looking at functions in Python, but not just how to write them. We're exploring why they are treated as first-class citizens. This means functions behave exactly like regular variables. Let's look at the code. Part 1. Functions are objects. Every function in Python is an object behind the scenes, meaning it has its own built-in attributes and metadata. Okay, we can inspect its name and docstring directly, or even assign it to a new variable. Like this. And output, let's print output in part 2, callables and underscore call underscore. To check if an object can be executed, Python uses callable functions return true because they contain a hidden magic method called call. Okay, let's print. Okay. Part 3. Passing functions as arguments. Since functions act like variables, you can pass them as inputs into other functions. This is perfect for building wrapper tools or logging systems. excuse me. Okay, let's run and print. Part 4. Advanced trick, flipping map. Instead of mapping one function over multiple numbers, we can flip the logic and map a list of functions over one piece of data. Print and output like this. Let's run. As you can see, functions are dynamic objects that give Python incredible flexibility. Don't forget to like and subscribe. See you. Number 1. Nested functions and scope. Functions in Python can be defined inside other functions. Inner functions exist only within the scope of the outer function and can freely access its variables. Like this. Okay. And the end of, excuse me, and the end of print. Okay, let's run and output like this, as you can see. Okay. Number 2, factory functions. When an outer function returns the inner function itself without parentheses, it acts as a dynamic function factory, like this. And return. Okay, another return. Okay, and creating custom functions. And print. Another print. Okay. Print. The output like this. Let's run. And as you can see. Number 3, forcing anything to be callable. Using nested functions combined with args and coargs, we can easily wrap a static fallback value into a function so our application never crashes when expecting a callable. Like this. Return element. Okay. Return element and return again. Okay, testing. And let's print. And let's print. The output like this, as you can see. Let's run. And as you can see, okay. Number 4, function monitoring. The logic behind decorators. By passing a function as an argument to an outer function, we can use an inner function to intercept, monitor, or log behavior before and after executing without touching the original code, like this. Let's print. Okay. And return result. Another return. Okay. Let's print. Print. Okay. And output like this. Subscribe for more Python tips. Today we are mastering 2 essential Python features: handling infinite arguments with star args and turning custom objects into functions using call. Part 1. Infinite arguments with star args. Use star args when you don't know how many items your function will receive. Python automatically packs these arguments into a tuple. For example, print and print. Okay. Return. Then example 2. And let's print and let's run and print. Excuse me. Let's print. Okay. Unpacking lists. If your data is already inside a list, unpack is directly into the function using the star operator, like this. Okay, let's print. And let's run and print. Okay. Rule. Positional arguments like discount must always be defined before star args. Part 2. Callable objects with call. In Python, you can make custom class instance behave exactly like functions using the double underscore magic method call. Unlike normal functions, these objects can remember their state and adapt dynamically, like this, for example. Okay. Let's return. Okay. Step 2, print, and output like this. Let's print and output like this. Okay, let's run. As you can see, okay, changing a state on the fly. Because it is an object, you can dynamically update its attributes to change its behavior like this. Let's print and print and output like this. Run, as you can see. Okay, summary. Star args handles a variable number of positional arguments as a tuple. Underscore call underscore gives your custom classes the simplicity of a function call with the power of object state management. Subscribe for more Python tips. Understanding quarks dictionary packing. Use double asterisks to accept an infinite number of named key value inputs. Python captures them inside a dictionary. For example, okay, calling with name arguments, okay, unpacking an exciting dictionary using asterisks. Okay, let's run and print. Excuse me. Oh, and print. Combining args and quarks, the strict order. The golden rule for combining arguments, standard variables first, followed by args, and quarks always comes last. For example, and valid positioning, okay. Critical error. You cannot pass a positional argument a raw value after you have started passing keyword arguments. Advanced boundaries using a slash and asterisk. Enforce how arguments must be passed using these two divider symbols. Before the slash, strictly positional only variable names cannot be used. After the asterisk, strictly keyword only variable names must be explicitly written. In between, standard parameters can be passed using either method. For example, okay, as you can see, and valid calls, invalid calls, Okay, and let's run. Let's run and let's print. If you help, subscribe for more videos. Got a memory error in Python? That's because lists are greedy. They load everything into your RAM at once. Today you'll learn how to fix this using generators. They are lazy, meaning they generate data on the fly, exactly when you need it. Let's look at the code. The core concept, the magic of yield. Unlike return, which kills a function, yield pauses it. Let's build a simulated leave server metrics stream. Look at the code. Okay. Calling the function gives us a generate object to pull data out of it step by step. We use next. Look at the code. Excuse me. The output like this. Okay. Print next string. Output like this. Let's run as you can see. Okay. The secret. The function literally freezes at the yield line, keeping its state alive until you call next again. Now the grand trade-off, memory versus CPU. Least fast to access any item instantly, but consumes massive memory. Generators consumes almost zero memory, but requires a microsecond of processing to calculate each item on demand, creating infinite data streams. Because generators don't store past data, you can run infinite loops without crashing your system. Let's make an infinite secure token generate. Look at the code. Excuse me. Import here. Okay. We can consume this infinite stream safely using a for loop with a break condition. Look at the code. Excuse me. And then break. Okay. Advanced applications, exponential tracking. Generators are perfect for tracking data that grows exponentially. Here is a custom step generator. Look at the code. Okay. We can track these generations cleanly by pairing our generator with Python built-in enumerate function. Look at the code. And let's print. Okay. And print it. Okay. The output. Summary. List, pre-compute, and store everything. Memory heavy. Generators compute items on one at a time, on demand, memory efficient. Yield pauses the function state instead of terminating it. Like, subscribe, and drop a comment below on what Python topic you want to see next. Happy coding! Generator expressions. While list comprehensions build list immediately in memory, generator expression use lazy evaluation, calculating values only when requested. Simply swaps square brackets for parentheses. Look at the code. Okay, the list comprehension, the generator expression. Okay, the output like this. And let's run, as you can see. Okay. Repeater. The output like this. As you can see. Okay. The pipeline pattern, lazy chaining. You can chain multiple generator expressions together to process data step by step. No actual calculations occur until you consume the final generator, making this incredibly memory efficient. Look at the code. Step 1. And step 2. Okay, step 2. Excuse me. Okay. And step 3. Okay. Let's print and output like this. Okay. Let's run, as you can see. Okay. Number 3, creating custom iterator with classes. For complex state management, you can build an iterator class. Your class must implement the itertool protocol. __iter initiates the loop, returns self. __next fetches the next value or raises a stop iteration to stop the loop. Look at the code. self current equal start, self stop equal stop, and then, excuse me, okay, return self, okay, next, excuse me, and then return result, okay, print val, and output like this. Let's run, and as you can see, look at the code. Okay. Number 4, the ultimate trade-off, memory versus speed. Memory benchmark. Generators use almost zero RAM because they don't store values. Look at the code. Imports. First import. Okay. Then 1,000,000 squared numbers. And print the output like this, and print the output like this, run like this, and like this. Okay, as you can see, a speed benchmark. Lists are faster because they are optimized in C. Generators run slower due to the overhead of calling underscore underscore next underscore underscore for every single element. Look at the code. First, import C profile. Okay, then print cprofile.run, then print, and then cprofile.run again. Okay, let's run. As you can see, 0.098 seconds in list. Generator 0.201 seconds. Okay. Summary. In memory in list, high growth with dataset size. Memory in generator, low constant O1. Speed in list, faster C-level optimization. Speed in generator, a slower function call overhead. Best for in list, a small data indexing, reusing values. Best for in generator, gigantic datasets, log streams, infinite sequence. Okay, subscribe for more Python tips. Python functions are first-class citizens. You can pass them as arguments and return them from other functions. A decorator is simply a wrapper function that dynamically enhances or modifies the behavior of a target function without permanently altering its source code. Building a timer decorator. Instead of hard-coding logs, we will build a universal performance timer decorator using args and coargs to accept any function parameter. Look at the code. Step 1. Create the decorator function that accepts the target function. Okay. And excuse me. Step 2. Define the inner wrapper function. Like this. Action before execution. Execute the actual target function and capture its return value. Action after execution. And then return result, return the actual result, return wrapper, return the modify wrapper. Okay. The @sign syntactic sugar. Instead of manually wrapping functions, Python offers the elegant @sign syntax to apply decorators instantly. Look at the code. Manual wrapping. And excuse me. Then the clean way. The clean way like this. Okay. The clean way. Now just call it normally. Excuse me. Okay, let's run and print. Okay, fixing metadata with functions.wraps. When wrapping a function, it loses its original identity. To preserve the original function's metadata for debugging and documentation, always use @wraps from the functions library. Look at the code. First import library. Okay. Then okay, this magic line copies the original metadata. Return result, then return wrapper. Okay. Summary. Use decorators to keep your code dry. Don't repeat yourself by isolating concerns like caching, logging, or authorization. Always implement wraps in production. Create custom decorator. Like, subscribe, and share your thoughts in the comments below. Hello everyone! Today we are exploring one of the biggest traps in Python, decorator stacking order and how to easily build parametric decorators. Let's jump straight into the code. The stacking order trap. Imagine we have function to post user comments and we want to do two things to it. First, censor bad words, and second, convert the out to uppercase. Look at the code. Return. Okay, return wrapper. Okay. Then okay, return wrapper. Now let's stack them on our function in this specific order. Look at the code. Excuse me. Let's print the output like this. Okay, let's run. As you can see. Okay. Why did the censorship fail? Because Python decorators execute from the bottom up. Close the function first. First, censor bad words, replace hate with a heart emoji, but then shut run and turn the entire string, including the emoji mechanism, into uppercase. Breaking it. If you flip the order, the next becomes uppercase first, meaning censor bad words won't find the lowercase word hate. Always remember the onion layer rule of stacking. Creating a decorator factory, passing parameters. What if we want to pass the specific word we want to censor as an argument? In a standard Python, we have to create a decorator factory using 3 levels of nested functions. Look at the code. Layer 1, then layer 2. Okay. Layer 3. And return. Return wrapper. Then return decorator. Okay. Now we can dynamically chain and pass arguments to our custom decorator. Look at the code. Okay. Return. Then print. The output like this. Excuse me. The output like this. Print. Okay. The clean way using the decorator library. Writing 3 layers of functions in exhausting To keep your code flat and readable, just install the decorator library using pip install decorator and write it cleanly in a single layer. Look at the code. First import library. Okay, then result and return result.replace. Okay. Now you can use it effortlessly like this. Return and let's print. The output like this. Okay, let's run. As you can see. Okay. Outro. Decorators execute from the inside out bottom to top for arguments. Either build a 3-layer factory or use the decorator package for cleaner code. Smash that like button, subscribe for more quick programming tips, and I'll see you in the next one. Happy coding! Ever wrote a Python script that starts offline but chokes on large data? The issue isn't Python. Your code is just suffering from amnesia. It keeps recalculating the exact same steps. Today, let's give your functions a permanent super memory using functools. The problem: grid traveler. Instead of textbook examples, let's look at a drone routing problem. We want to find all unique paths from the top left to the bottom right of a grid, moving only down or right. Look at the code. Okay, for a small grid, it's instant, but try a 18 at 18 grid and your terminal freezes. Why? Because it recalculates the exact same subgrades thousands of times. It's pure madness. Look at the code. Let's run and freeze terminal. Okay. Comment. The solution: LRU cache. Instead of rewriting the algorithm, let's just use Python built-in LRU cache. First, import library. Then, LRU cache, max size 128. Okay, print. Let's run. And boom! Milliseconds LRU stands for least recent used. It saves result in a box. The max size 128 parameter limits the box size to save RAM, throwing away old result when full. Perfect for keeping memory usage predictable. The shortcut: if you don't care about memory limits and just want infinite string, use cache. First, import library. Then, instead LRU cache. excuse me, comment cache, and let's run and print. Okay, this is just shorthand for max size noun. It's the ultimate make my function fast button. The pitfall. One major cache, since caching use a dictionary under the hood. All arguments must be hashable. Look at the code. To fix it, pass mutable object as immutable tuples instead. Okay. Pass a list or dict, and Python crashes. Always use tuples or strings here. Like, subscribe, and tell me in the comments which one you'll use. See you. Hello everyone. Want to make your Python code shorter, cleaner, and more professional? Today we're ditching ugly for loops and repetitive arguments using two powerful tools from the functools module, reduce and partial. Let's jump straight into the code. First, reduce. It applies a function to a list of items sequentially, 2 by 2, until the entire collection is condensed into a single final value. Let's build content filter to swap out spam keywords. The traditional way use a for loop. Look at the code. And print the output like this. Let's run. As you can see. Now, let's look at the elegant way using reduce. First, import library. Okay. And let's print. Let's run, as you can see. Okay, super clean. Reduce takes our lambda function, runs it through the banned words. List starts with the raw comment as the base, and update the text step by step until it returns the final clean string. Next up is partial. If you have a function that takes multiple parameters, but you find yourself repeating the exact same arguments over and over, partial allows you to freeze those arguments and create a new specialized function. Imagine a generic alert function. Okay, let's print. Okay, if we are writing code inside a payment module, the first two parameters never change. Look at the code. Instead of repeating ourselves, we can use partial to lock those values in. Let's run. Okay. First, import library. Then, creating a new specialized function with fixed parameters. Now we only pass the remaining unique argument. Let's run and print it. Okay, print it. Now, log payment critical only requires the unique message. It makes your code cleaner and cuts out human error. Let's combine both tools. We can freeze our reduce operation inside a partial function to create a highly reusable utility tool. Look at code. Okay. Comment 2. Let's print comment 1. Output like this. And print comment 2. Output like this. Let's run. As you can see. Okay. That's the power of writing functional Python code. We built a dedicated text cleaner tool with zero boilerplate. Remember, use partial when you want to lock in repetitive arguments, and use reduce when you need to condense a list into a single result step by step. If you like these advanced Python tips, make sure to subscribe and hit that like button. See you in the next one. Ever wondered what obscure number like status equal 3 mean in code? These are magic numbers, and they make code hard to read and prone to bugs. Today we'll fix this using Python enums to write cleaner, safer, and self-documenting code. Let's get straight into it. Instead of using loose string or integers, we can group related constants into a dedicated type. Let's import enum and create a status tracker for a project app. Look at the code. Okay, now we can assign a status cleanly. When you print it, Python treats it as a strict type, not just a random numbers. Look at the code. Okay, let's print. And let's print. And let's run. Okay, output like this. Every enum member gives you two critical properties: dot name for the string representation and dot value for the underlying data. Look at the code. The output like this, and output like this, and print. Let's run and print it. Okay. Because Python enums are actual classes, you can add custom behavior to them. Let's implement the __add __ magic method, so using +1 automatically advances our task status to the next step. Okay, in this class here, then return and return. Okay, let's test this logic inside a simple workflow loop. Okay, let's run and let's print. Perfect. The workflow logic now lives cleanly inside the enum itself, keeping the rest of your app completely decoupled. If you don't care about the exact integer value and just need unique names, don't type numbers manually. Use auto instead. First, import library, then okay. Python dynamically assigns sequential numbers under the hood. If you insert a new tier later, Python recalculates the order automatically without breaking any external code. If you must assign values manually, like specify hardware bitmasks, human error can lead to duplicate values. By default, Python allows duplicates as aliases, which can cause silent bugs. Look at the code. Okay. To catch this instantly, protect your class with the unique decorator. It forces Python to throw a value error the moment a duplicate occurs. First, import library, then okay, run error. Okay. Use auto when values don't matter, but always use unique if you are writing values by hand. That's how you write robust constants using Python enums. Like the video, subscribe for more quick Python tips, and drop a comment below. See you! Ever wondered what the actual difference is between regular methods, class method, and a static method in Python? In this video, we're breaking it down once and for all using a spaceship simulator example. Let's dive right in. First up, instance methods. These require a concrete object to run and use self to access that object's unique data. Look at the code. Okay. Let's print. Okay. Else print. Okay. Excuse me. And print. And print. Okay. When you call my ship fire laser 20, Python automatically passes my ship into self. You must create an instance to use it. Look at the code. Okay, let's print. Let's run and let's print. Okay. Class method marked with @sign class method. They receive the class itself CLS instead of an object instance. They are perfect for building alternative initializers factory methods. Look at the code. In here. Here. Okay, now we can create pre-configured ship directly from the class without manual setup. Using CLS ensure it remains safe for future inheritance. Look at code. Excuse me. In here. Let's print. Okay, let's run and print it. Okay. Static methods defined with @sign static methods. They are completely isolated. They don't take self or CLS as parameters. They are just regular utility functions living inside the class for neat organization. Look at the code in here. And return. Okay. You can call it instantly without managing any object states. Here. The output true. The output is false. Let's run. As you can see. Use instance method self for individual object behavior, class methods CLS for classes level actions like alternative initializers, and static methods for a standalone utility function. If this helped, hit subscribe, leave a like, and drop a comment down below. See you next time.